So very good evening to everyone. Today we will be discussing about the biomass pre-treatment processes and the necessary of the pre-treatment processes for utilizing the biomass in the biorefinery. So getting started with today's session, I would like to give a brief introduction about the biomass pre-treatment process, why it is necessary, and how we should do the biomass pre-treatment. So, the increased worldwide demand for the energy, and particularly from the petroleum derived fuels, that has led to the search for the long term solution of reliable source of clean energy. So we need clean energy. For that, we are looking for the biomass to utilize as a full extent to derive various fuels from the biomass clean sources. In that context, we already discussed in the last class that the lignocellulosic biomass has the full potential to produce the biofuels, which are very um, like which are very close uh, fuel characteristics like the petroleum based fuels. Okay, so lignocellulosic biomass that appear to hold the key for a continuous supply of the renewable fuels without compromising with the increase of energy needs. So, the major possible solutions to the current energy crisis include the ethanol production, bio oil production, and the synthesis gas or syngas production from our clean source, that is lignocellulosic biomass. So, in this session, in this today's class, we are mostly focusing on the lignocellulosic biomass as our clean source of energy, clean source of the energy. So lignocellulosic biomass we are choosing or defining in such a way that it has the full potential energy production potential. That's why we are focusing mostly on the lignocellulosic biomass, and the lignocellulosic biomass are easily available. So, lignocellulosic biomass is usually categorized into agricultural crops or forest crops. Dedicated energy crops are also included. Even the wood residues from the soft and hardwood, as well as the municipal paper waste or any kind of municipal green waste, that we can also consider as a lignocellulosic biomass source. So, a kind of non-renewable lignocellulosic feedstock is also accessible, which is also referred as the disturbance wood or crops that are typically forest and crop resources damaged by insects, pests, and diseases. So these kind of crops we cannot use for the for the food supply or the food chain maintain. So these kind of damaged crops are also are not being considered to be as a waste anymore. So it can also be utilized for the production of the bioenergy. Effective utilization of the lignocellulosic biomass, we need to consider pretreatment as a very essential and necessary process as the first process to reduce the recalcitration of the lignocellulosic biomass property. Now, the pretreatment process, which plays a very significant role, it attenuates the accessibility of the cellulase, which is an enzyme, for various enzymatic hydrolysis processes by disrupting the lignin, hemicellulose, and cellulose. It has a very complex structure. So pre-treatment process, while we are doing various, we are opting for the various methods for the pre-treatment of the biomass to make it more accessible for the enzymatic hydrolysis, so that we can disrupt the uh, complex structure of the lignocellulosic biomass. So, the pretreatment process is also considered as the second most expensive step in a biorefinery after the enzymatic hydrolysis for the conversion of lignocellulose. So, it also invest lot of money for in the biorefinery, because we are doing lot of chemical treatment as well as physical treatment for making the biomass less recalcitrant in nature. So, in the conventional pre-treatment methods, lignin was not well solubilized in a liquid phase. When we are considering normal conventional pretreatment methods, so the lignin is not well solubilized in the liquid phases, thus those are not readily recovered as a clean lignin stream for the further utilization. So, for the successful utilization of the lignin as a co-product, a clean and high quality lignin stream is very necessary for it. So, for this purpose, a promising approach to address this lignin issue is to enhance the acid-base hydrothermal aqueous pretreatment method, which is a very advanced method by adding the organic co-solvents. That is the organosolvent method that we will be discussing in the further slides. So, this is a very promising approach to address the lignin issue, which is very common in the lignocellulosic biomass. So it will disrupt the biomass structure and fractionate the biomass polymer macromolecules for the downstream processing, and allowing it more for relatively pure and non-condensed lignin stream can be easily separated out of that. So now we will consider more about some barriers that we are talking from the last two classes, that what are there are some challenges or barriers when we are dealing with the lignocellulosic biomass for the conversion to biofuels, right? Um, okay. So the lignocellulose, when it is we are considering as a complex structure, it is major components. Uh, it is a major components for the plants that provides them the structure, as well as it is present in the root, stalks and leaves. So the the plant cell walls are primarily made up of cellulose, hemicellulose, and lignin. So in there we can see that they are the main uh, elements are carbon, hydrogen, oxygen, and also there are some complex structure you can see in the lignin. So these are some chain-like structure of these repeating units. We will discuss in the next slide. So there are other elements are pectin and glycosylated proteins. So when we are considering on the dry matter basis weight percentage distribution, so typically the lignocellulosic biomass has 30 to 60% cellulose in nature, 20 to 40% hemicellulose in content, and also 15 to 25% lignin in content. It is based on the dry matter basis. So the lignocellulosic, it forms a complex crystalline structure which held together by the covalent bonding. So there are some intermolecular bridges as well as van der Waals forces that make the lignocellulose more hydrophobic in nature. Also, uh, uh, henceforth it is insoluble in water and it is very difficult to attack by the enzyme, so it is very difficult to dissociate even. So these are some barriers that we are mainly facing while we are dealing with the conversion of or the um, breaking the lignocellulosic biomass into a small fraction or the simpler version. So we are facing as a barrier that the crystalline structure is very hydrophobic in nature and very tough to attack by the enzymatic actions. So, due to the non-fermentable nature of the lignin, basically, the biomass pretreatment is very necessary to separate the cellulose, hemicellulose, and lignin so that we can process for the selective operation in the downstream processes. So, biomass recalcitrance has been mitigated in part by advanced pretreatment system. There are various advanced and emerging pretreatment systems that can alter the structure of the lignocellulosic biomass. They can alter the binding nature and the composition of the biomass components as well. In a typical cellulose ethanol production, we are considering ethanol as a product here. Focusing on it, the lignin is considered the predominant recalcitrant component for the component of the plant cell wall. So it is mainly the predominant recalcitrant it is offering, and it is resisting for the delignification. So therefore, delignification significantly benefits. So when we have to improve the delignification process, we have to separate the lignin from the cellulose and hemicellulose, or vice versa, so that we can give the benefit for the conversion of the carbohydrate fractions in the biomass to the efficient fuel conversion. So we have to separate the hemicellulose, cellulose and lignin in a proper way through the pretreatment processes. So when we are considering the lignocellulosic biomass, so we need to understand that what are the properties of these three components, that is cellulose, hemicellulose and lignin. So we will be discussing now the three components in details, and we will discuss a little bit detail in their structural differences and their main derivatives that we can get out of those three different components. Okay. So first we are going for the cellulosic biomass. So the most abundant naturally occurring organic and high molecular weight polymer in the world is considered cellulose. So it is the most high molecular in weight and highly most abundantly available in the nature. So it is the major structural material in the plant cell. Whatever be the plant cell, it is the major structural material that we can say. And because of the large fraction of the cell wall is made from the cellulose, and this structure provides the plant to be stable even in the absence of the water, as well as being it renewable and biodegradable as well. So the basic structure of cellulose is linear in nature. It consisting of the homopolymer of the anhydroglucopyranose monomeric units that are connected through beta 1,4 glycosidic linkage. The standard structure of cellulose is a long chain polymer of the D-glucose, which is a sugar, and as it is repeating unit that is formed by the unbranched chains. Okay. So depending on the source, the degree of polymerization of the plant cellulose could be between 7,000 to 15,000 glucose molecules are there in the cellulose. So cellulose is crystalline in nature. So due to the crystalline structure, the cellulose fibers are very difficult to be degraded. Natural cellulose is hydrophilic in nature, and changes their character will cause loss of mechanical property on moisture absorption. The complex structure arrangement of this cellulose has caused materials such as enzymes and even water can hardly penetrate into the fibers because of this complex crystalline structural arrangement. The structure of cellulose are not completely crystalline, to be truth. matlab, to be in nature, it is not completely crystalline. The structure characteristics has micropores as well, with amorphous in nature, which will be the point of attack for the cellulolytic and enzymes to enzymatic hydrolysis. The next one is the next one. What we are going to discuss about, that is hemicellulose. Hemicellulose, those are the degree of hemicellulose is between 80 to 200 of different pentose and hexose sugars. There are different combination of the pentose and hexose sugars. So its structure is branched polymer with low molecular weight. It is the second most available polymer in the world after cellulose. Okay. So typically the hemicellulose is formed by a group of homo and as well as hetero polymers. A high degree of side chain substitutions on the hemicellulose main chain binds less tightly to cellulose and becomes more water soluble. Hemicellulose, when we are talking about, it is mostly thermochemically sensitive. So it is a complex hydrocarbon structure which serves as a bridge between the lignin and cellulose fibers, and it gives the whole cellulose hemicellulose lignin network more rigidity. So the dominant component of the hemicellulose is xylem in the hardwood and agricultural plants and grasses as well, while glucomannan is the dominant components of the cellulose hemicellulose in the softwood. The hemicellulose that reduce the mean pore size of the biomass, therefore it reduces the accessibility of the cellulose to hydrolytic enzymes. It reduces the mean pore size if the hemicellulose content is more. Mostly, it is reported that the hemicellulose is chemically linked or cross-linked with the polysaccharides, proteins, and other lignin. The major interface of lignin and other carbohydrate is the xylene that mostly occur. The xylene in the hemicellulose can be extracted quite well by the acid or alkaline treatment, pretreatment method, while the glucomannan can hardly be extracted in the acid environment and it needs very strong alkaline environment than the xylene. So these are some important factors for the hemicellulose content of the lignocellulosic biomass. Next, it comes the lignin, most important part, which is a main recalcitrant property holding the component of the lignocellulosic biomass. So it is the third most available natural polymer after the cellulose and hemicellulose, and it corresponds to 15 to 40% of the dry weight percent. It is a heterogeneous and complex and highly cross-linked large aromatic polymers which is with substituents connected by both ether and carbon-carbon linkage. So lignin is an amorphous polymer consisting of phenyl propane units, and their precursors are three aromatic alcohols, namely para paracarbonyl or alcohol, coniferyl alcohol, and synaptyl or alcohol. So the lignin makes the cell wall very rigid in nature, despite the lignin structure itself made it as the most recalcitrant polymer to process. The energy content in the lignin is very high. Upon separation of lignin, the lignin can be burnt to produce electricity because it is highly energy dense material, as well as it can produce other chemicals. So it is, we need to efficiently separate the lignin from the cellulose and hemicellulose content. First of all, lignin can physically limit the polysaccharide accessibility to the enzymes, and it plays an important role as a physical barrier because it blocks the accessibility of the enzyme to the cellulose. Also, it can irreversibly adsorb cellulases, that is the enzymes and other enzymes during the enzymatic hydrolysis due to its hydrophobic structural features including hydrogen bonding, methoxy groups and polyaromatic structure. So it can adsorb the these kind of enzymes, and these are irreversible process. So thus they make the process the physical barrier um, for the degradation of cellulose by enzymatic hydrolysis. So you can see in this picture that these are the polymers or main components of the lignocellulosic biomass. Cellulose, these are repeating units, and uh, it can connect to the hydrogen bonding. There are lot of hydrogen groups, OH groups are present on the surface, so these may form the hydrogen bonding with the other molecules. So the main depolymerization product we can get from the cellulose, that is D-glucose. Whereas in the hemicellulose, you can see that there are this kind of structure branched. These are linear structure we are getting here, and here we are getting some branched kind of structure. Okay, so in this there are also available OH groups are present in the on the surface. It can also make the hydrogen bonding. So on the depolymerization product we will get mostly the monosaccharides and the uronic acids. Glycerin, it is more complex in nature. You can see that molecular structure is more complexer than the same cellulose and hemicellulose. And the main depolymerization product we can get, those are phenol derivatives. Various kind of phenol, because this is aromatic, mostly aromatic in nature. So we are getting the derivatives, those are phenol derivatives. We'll discuss about the importance of the pretreatment processes for the lignocellulosic biomass. For the conversion of biomass to the biofuel, the cellulose and hemicellulose must be broken down into their corresponding simpler sugar forms or the monomers. So the advanced pretreatment processes, they allow to change the structure of the lignocellulose, such as increasing the surface area and increasing the porosity of the biomass. Otherwise, they can modify or remove the lignin content, partially polymerize or removes the hemicellulose out of the lignocellulosic biomass content, or it can also reduce the crystallinity of the cellulose. So these are some basic target of the pretreatment processes. So the pretreatment will render and make the cellulose fiber more easily accessible to the enzymes to bind and hydrolyze those cellulosic fibers. So you can see from this picture that the wall of the cell, plant cell, is made of lignin, which is mostly inner side there is chain-like structure, those are cellulose in nature, and mostly branched structures are hemicellulose in nature. So this complete region is amorphous region, and this is complete considered to be crystalline region. So in this complex structure we can see that after pre-treatment these are fractions, like fractionized in proper ways, and easily accessible in nature. Easily accessible fractions are there after the pre-treatment process. So this is the basic purpose of doing the pre-treatment, so that we can do the downstream processing in a efficient way, because if the lignocellulosic biomass we are putting it in a complete as a whole for the, suppose we are doing the pyrolysis of the biomass, lignocellulosic biomass, and we are not fractionating or we are not segregating the lignin cellulose and hemicellulose content, so the overall yield of the biomass, overall yield of the biofuel production from that lignocellulosic biomass as a whole will be less. But if we are doing the modifications or the advanced pre-treatment processes, we are following those processes or steps, then we can increase the yield of biofuel production. So, what are the most important parameters for considering or selecting the pre-treatment processes? First one is the biomass crystallinity. So different types of biomass from the woody plants, for herbaceous plants or grasses or aquatic plants. So these kind of plant based or biomass based biorefinery concept I have already discussed in the previous classes. So these residues or municipal solid waste, or suppose you are considering the manures, they contain different compositions of cellulose, hemicellulose and lignin. So these all are different because the compositional variations are always present, and there are other difference in the other extractives, right? So however, the main components that we are considering or focusing here, that is the main polymer cellulose, hemicellulose and lignin. The cellulose in any biomass is found to be present in two forms, namely amorphous in nature or crystalline in nature. So the crystalline cellulose core of the cell wall microfibrils is highly resistant to the chemical and any kind of biological hydrolysis because of their structure. Because this is mostly highly crystalline in nature, in which chain of cellodextrin are precisely arranged. So the decrease in the crystallinity may increase the digestibility of the lignocellulose. So we need to focus on the process or possibility for decreasing the crystallinity of the biomass, so that that is more accessible for the digest of the lignocellulose. So next one is the hydrophobicity of the crystalline structure of the cellulose, which also makes it more resistant to the acid hydrolysis because it forms a dense layer of the water near the hydrated cellulosic surface. Now the strong interchain hydrogen bonding network that I already discussed in the last slide, that how the hydrogen bonding is occurring because of the functional groups are present on the surface of the molecular structure of cellulose. So they make interchain hydrogen bonding network also makes the crystalline cellulose resistant to the enzymatic hydrolysis, whereas the hemicellulose and amorphous cellulose are readily digestible. The degree of the crystallinity of the suppose considering an example, that the degree of the crystallinity of the corn stover increased from 43 to 60% through our this kind of delignification processes with the help of alkaline pretreatment, that is the calcium hydroxide pretreatment, due to the removal of the amorphous components like lignin and hemicellulose. So they have removed the uh, hemicellulose and lignin from the cellulosic content, and thus the degree of crystallinity increased through the delignification process by this pretreatment um, approaches. So the next part is the degree of polymerization. So the degree of polymerization and cellulose crystallinity have been considered as the most important factor in determining the hydrolysis rates of the relatively refined cellulosic substrate. In the enzymatic hydrolysis condition, the endoglucanases target at the internal sites of the cellulosic chain, which is primarily responsible for decreasing the degree of polymerization of the cellulosic substrate and making it more prone to the uh, degradation of the cellulose. So it is suggested that the hemicellulosic removal had more severe impact on the cellulosic chain length than the lignin removal. So hemicellulosic removal is mostly um, suggested than the lignin removal. The other point is the accessible surface area. It is important factor in the lignocellulosic material because it plays a very significant role in the enzymatic hydrolysis process. The surface area in the lignocellulosic material can be categorized into external and internal surface area. The external surface area is related to the size or shape of the particle, while the internal surface area depends on the capillary structure of the cellulosic fibers. So an important factor is that pore size of the substrate plays very important and limiting factor in the enzymatic hydrolysis of the biomass. So removal of the hemicellulose that increases the mean pore size of the substrate, and therefore that will increase the probability of the cellulose to get more hydrolyzed. So that's the removal of the hemicellulose is very efficient for getting the more efficient enzymatic hydrolysis. Drying of the pretreated lignocellulose can cause a collapse in the pore structure, so they may result in a decreased enzymatic hydrolysis rate. So again, upon drying the pretreated lignocellulose, that may adversely impact on the enzymatic hydrolysis condition. However, it was shown that the cellulose surface area is not a major limiting factor for hydrolysis of the pure cellulose. When we are considering the pure cellulose is not a very big factor surface area, but when we are considering a complex structure of the cellulose, hemicellulose and the lignin, so it is advisable to remove the hemicellulose content as a first step to get more benefited enzymatic hydrolysis. Next one is the lignin and hemicellulosic contents. So the relationship among the structural and compositional factors that reflects the complexity of the lignocellulosic biomass matrix. Generally, the plant biomass that consists 40 to 50% cellulose, with exception to few plants like cotton and hemp bast fiber that made up mostly 80% of cellulose, and other mostly containing for 20 to 40% hemicellulose and 20 to 30% lignin by weight. Lignin restricts the rate and extent of the enzymatic hydrolysis by acting as a shield, and it prevents the digestive parts of the biomass from being hydrolyzed. The delignification process that can improve the rate of this hydrolyze and the extent of the enzymatic hydrolysis condition. However, the solubility of the lignin in the acid, neutral or alkaline environment depends on the precursors of the lignin, namely paracoumaryl, coniferol and synapyl alcohol and the combination of them. So these kind of precursors are also play important role when we are doing this kind of acid or alkaline treatment of the lignin content. So now we will discuss about the different pretreatment methods, including physical, chemical, and physico-chemical other treatment strategies. So the physical pretreatment is used to increase the accessible surface area and the pore size of the lignocellulosic contents, and it also helps to decrease the crystallinity and the degree of polymerization of the cellulose present in the lignocellulose, and which helps to degrade the cellulosic content in a better way. Different types of physical processes are in practice, such as milling. Uh, in the milling, there are options like ball milling, two roll milling, hammer milling, colvade milling, and vibro energy milling. These kind of operations are energy expensive. Anyways, there are other options like chipping, grinding, irradiation. Irradiation includes gamma rays and electron beam irradiation. This can be used to improve the enzymatic digestibility of the lignocellulosic waste material. So the size reduction is one of the most effective methods for increasing the enzymatic accessibility to the lignocellulose. One of the novel method that is extrusion, and it is also promising a physical pretreatment method for the biomass conversion to the biofuel production. So in extrusion method, materials are subjected to heat, mix and shear, which result in the physical and chemical modifications as well in the biomass after processing through the extruder. Next pretreatment process, that is the chemical pretreatment process. It has become one of the most promising method to improve the biodegradability of the cellulose by removing the lignin or by removing the hemicelluloses, and to decrease the degree of the polymerization and decrease the crystallinity of the cellulosic component in the lignocellulose. So the chemicals ranging from oxidizing agents like oxidizing agents or alkali or acid or salts that can be used to degrade the lignin, hemicellulose and cellulosic content from the lignocellulosic waste. Organic acids are also used, such as oxalic acid or acetyl salicylic acid or salicylic acid can also be used as a catalyst, while an organic or aqueous organic solvent mixture like inorganic acid mixture with the organic solvent is also used to break the internal lignin and the hemicellulosic bonds. However, concentrated acids are not preferred because they are very corrosive in nature, and this kind of acid, whatever you are using in the pretreatment method, that must be recovered to make the pretreatment economically feasible. Next, we are talking about the physico-chemical pretreatment method. So, this kind of pretreatment combines the physical process as well as chemical process, and these are giving greater importance in dissolving the hemicellulose and alteration of the lignin structure, which provides an improved accessibility of the cellulose for the hydrolytic enzymes. It includes the vast majority of the pretreatment methods such as steam explosion, liquid hot water, or the um, auto hydrolyze auto hydrolysis, ammonia fiber explosion, wet oxidation, ammonia recycle percolation, aqueous ammonia organosolvent method, and carbon dioxide explosion. Recently, also ionic liquids and deep eutectic solvents as well, and other cellulose solvent-based lignocellulosic fractionation processes are being proposed. Recently, those are also being researched in a broader way. This type of pretreatment depends on the process conditions, solvents used in the process that affect the physical and chemical properties of the biomass. Next is the biological pretreatment method. The biological pretreatment is mostly associated with the action of different kind of fungi that are capable of producing different kind of enzymes to degrade the lignin, hemicellulose and polyphenols which are present in the biomass. His biological pretreatment it has attracted interest because of his potential advantages over the physical and chemical pretreatment methods, such as substrate and in the biological pretreatment, the substrate and the reaction specificity is higher. It consumes low energy and also there is no generation of the toxic compounds after the pre-treatment, and it also gives the high yield of the desired product, but it has a disadvantage, that is it takes longer time, very slow process, so it is not feasible for the higher production as well, but higher production in the sense quicker production, so it has that limitation it holds. But most lignolytic microenzyme microorganisms solubilize or consume not only lignin but also other hemicellulose and cellulosic content. Therefore, the biological pretreatment faces some techno-economic challenges and it found less attractive commercially. That I am talking about. That commercially it is not viable. The microorganisms, which are mainly brown, white, or soft rod fungi, and acetomycetes and bacteria, which degrade the lignin, hemicellulose, and very little portion of the cellulosic content. Several Several white rod fungi, such as this kind of fungi, these are mentioned, some of the scientific names of the fungi are mentioned. They showed high delignification efficiency on the different lignocellulosic biomass content. So in the next few slides, I am going to discuss about detail on the chemical pretreatment method, because after the physical pretreatment that is mostly focusing on the milling and size reduction process, the chemical pretreatment process is the uh, mostly eligible and effective methods for treating the biomass contents. So I am going to discuss in detail about the different kinds of chemical pretreatment methods available. The first one will be acid pretreatment. Second, I will discuss about the alkaline treatment. Third, there will be discussion on the steam explosion, liquid hot water treatment, or it is also known as auto hydrolysis, and there will be discussion on the ammonia vapor explosion, CO2 explosion, ionic liquids or deep eutectic solvents, organosolvent processes, lysis process, and wet oxidation. So, first one we will discuss about the acid pretreatment process. Acid pretreatment of the lignocellulose is very effective and well-known process to obtain a structure which is very suitable for the enzymatic hydrolysis. Now, the lignocellulosic ethanol production, if you are considering, that involves the acid hydrolysis followed by enzymatic saccharification using the cellulase enzyme. So acid pretreatment depends on parameters such as type of the acid you are using, acid concentration, solid to liquid ratio and temperature of that acid treatment. So the inorganic acids such as sulfuric acid, nitric acid, hydrochloric acid, phosphoric acid have been elaborated for lignocellulosic pretreatment method. Those are highly practiced. Dilute acid range from zero point 0.1 to 2 weight by volume percent are generally used in the acid pretreatment methods. This is the range for using those concentration of the acid, and the pretreatment using the sulfuric acid have been extensively used in various studies for its high catabolic activity. Acid pretreatment, it requires the high temperature and high pressure conditions for the effective pretreatment. Also, the dilute acid pretreatment is the most effective process for the lignocellulosic content, which generates lower degradation product and products than when we are using the concentrated acid. So, preferably the concentration is diluted and it is maintained zero point 0.1 to 2 weight by volume percent for effective production of the biofuel out of that and less generation of the degraded product. So it can be used either as a pretreatment of the lignocellulosic content for enzymatic hydrolysis, or it is the method for hydrolyzing the lignocellulose to fermentable sugars in two-stage acid hydrolysis. Acid pretreatment, it allows to hydrolyze the hemicellulose, especially xylene, present in the lignocellulosic content in a more percentage. Hemicellulose can be degraded into xylose, mannose, acetic acid, galactose, and glucose, etc. So, at a high temperature and pressure condition, often used in the industrial processes, where glucose and xylose degrade into degradation products such as furfuryls and hydroxymethanol methyl furfuryls respectively from this xylose and from this glucose and xylose content, and further degradation forms formic acid and levulinic acid from the acid pretreatment methods at a high pressure and temperature condition. All of these compounds of this degraded product, all of these compound have the negative impact on the downstream processes. So it is very crucial to remove of this degraded compound in an efficient way to increase to minimize the process cost in the downstream. The next point that we are going to discuss, that is the alkaline pretreatment process. The alkaline pretreatment is one of the extensively used chemical pretreatment method, which employs various alkali compounds such as sodium hydroxide, calcium hydroxide or lime, potassium hydroxide, aqueous ammonia, ammonium hydroxide and hydrogen peroxide in combination of this also is applied for effective pretreatment of the lignocellulosic content. Now, the alkaline pretreatment removes the acetyl group and various uronic acid substitutions in hemicellulose. So by removal of this acetyl group and uronic acid substitution, it increases the accessibility of the hemicellulose and cellulose to the two hydrolytic enzymes. So during the alkaline pretreatment, the reaction salvation and suffocation takes place, which cause swelling and leading to decrease in the degree of polymerization and crystallinity. So and it also helps to increase the internal surface area, not external, internal surface area, and it also disrupt the lignin structure and break the structural linkages between the lignin and the carbohydrates. Among the chemical pretreatments, alkali pretreatment provides the most effective method for breaking the ester bonds between the lignin, hemicellulose, and cellulosic contents, and it avoids the fragmentation of the hemicellulose polymers. Sodium hydroxide has been reported to increase the hardwood digestibility from 14% to 55% by reducing the lignin content from 24 to 55% in the range from 55 to 20%. So it is very effective method. Alkaline pretreatment is effective method for selective separation of the lignin from the hemicellulosic content, and thus it increase the digestibility of the biomass. Calcium hydroxide was found to be effective to remove the acetyl group from the cellulose that I have already discussed, and it also reduced the steric hindrance of the enzymes and enhanced the cellulose digestibility. The next one is the steam explosion. The steam explosion is considered to be a combination of the physical and chemical pretreatment method, which is nowadays mostly widely employed method for treating the lignocellulosic biomass. So during the treatment, the material is treated with the steam at a high temperature for few minutes to facilitate the subsequent enzymatic hydrolysis of the cellulose and hemicellulose to produce the monomeric hexones and pentose sugars. Steam explosion allows the removing of the lignin into a limited extent and redistributes the lignin on the fiber surfaces as a result of melting and depolymerization or repolymerization reactions. So the material is well impregnated with an acid prior to the steam explosion to increase the overall sugar, this pentose and hexose sugar yields. Acid So, steam explosion is typically performed at a temperature range of 160 to 260 degrees Celsius, while pressure is maintained 0.67. Sorry. The pressure is maintained as 0.69 to 4.83 megapascal for few seconds to few minutes, and the further material is exposed to the atmospheric pressure. The factors that affect the steam explosion pretreatment are residence time, temperature, biomass size, and the moisture content. So, the addition of the sulfuric acid or the SO2 content or the CO2, it is typically used in the steam explosion that decreases the time and the temperature of the reaction. It improves the hydrolysis rate and decreases the production of the inhibitory compounds, which leads to complete removal of the hemicellulose. It was reported an efficiency of 90% in the enzymatic hydrolysis of the polar chips pretreated by the steam explosion reported 90% of the enzymatic hydrolysis by the when it is pretreated with the steam explosion compared to only 15% hydrolysis of the untreated chips. So pretreatment is very necessary to increase the yield of the um, uh, biofuels. Steam explosion pretreatment was found to be advantageous due to low energy requirement and no recycling or environmental cost. The conventional mechanical methods it requires 70% more energy than the steam explosion to achieve the same particle size reduction. So it is the combination of the physical and chemical properties, pretreatment properties. So it is a very efficient method in the energy consumption in context as well as environmental context. It is very efficient for removing lignin in a limited extent and also increasing the digestibility of the cellulosic content in hemicellulose and cellulosic content to the monomeric hexose and sugar units. So the next one is liquid hot water or pretreatment method, or it is also known as auto hydrolysis. This liquid hot water pretreatment is very similar to the steam explosion, except for the use of the water, they use the liquid state. Except for they use the steam, and here it is used water in the liquid state at the elevated temperature only, 160 to 240 degrees Celsius instead of the steam. So, liquid hot water or the auto hydrolysis result in the hydrolysis of the lignocellulose. It removes the lignin and rendering the cellulose of the biomass more accessible while avoiding the formation of another inhibitory compounds that occur at a higher temperature. However, complete delignification is not possible by hot water alone due to recondensation of the soluble compounds originated from the lignin. This pretreatment offers several advantages that it does not include any catalyst or chemical. It requires low temperature. It doesn't require that steam formation, so it requires low temperature, so it minimizes also the degradation product formation. It eliminates the requirement of the washing step or the neutralization, and also it has low cost of the solvent for large uh, scale application. Additionally, biomass size reduction is not required here because the particles are broken down during the pretreatment, which makes the process more attractive for the large scale. Now, hot water it it destroys or destruct the hemiacetal linkages, thus liberating the acids during the biomass treatment, which facilitates the breakage of the ether linkage as well in the biomass. It is stated that the cleavage of the oxygen acetyl groups and uronic acid substitutions on the hemicellulose group could help or hinder the liquid hot water pretreatment method because of the release of this kind of acids. The acids that are releasing that may help as a catalyst. They catalyze the formation and removal of the oligosaccharides and further hydrolyze the hemicellulose to the monomeric sugars, which can be subsequently degraded to aldehydes, different aldehydes like furfural from the pentoses and HMF from the hexoses. The formation of these monosaccharides and the subsequent degradation catalyze the hydrolysis of the cellulosic material. So, this autocatalytic formation of the inhibitory compounds can be minimized by maintaining the pH of the process 4 to 7 in the range. So, the next method is the ammonia fiber explosion method. Um, Ammonia fiber explosion is also a combination of the physical and chemical pretreatment process in which the lignocellulosic biomass is exposed to liquid ammonia at a high pressure and temperature condition for a period of time, and then it is subsequently the pressure is reduced or it is exposed to the atmospheric pressure condition. The parameters that affect the ammonia fiber explosion process are ammonia loading, temperature, water loading, blow down pressure, time, and number of other treatment. The ammonia has a remarkable effect on the lignocellulosic, causing swelling and physical disruption of the biomass fibers, partial decrystallization of the cellulose, and breakdown the lignin carbohydrate linkage. During this pretreatment, only a small amount of the solid material solubilizes that ensure the loss of almost no hemicellulose or no loss of the lignin. So this pretreatment changes the structure of the biomass, which increase the water holding capacity and also thus increasing the digestibility of the biomass. The process could be significantly demonstrated for the saccharification and fermentation rate of various herbaceous crops and grasses as compared to the woody biomass. Recently, this ammonia fiber explosion method has been successfully used in simultaneous saccharification and co-fermentation processes using recombinant this Saccharomyces cerevisiae and these strains obtaining high ethanol yield from sweet grasses and corn stover. So this is very effective method for um, simultaneous saccharification as well as co-fermentation. Further, this ammonia which is used in the ammonia fiber explosion can be recycled after the pretreatment, which enhances the process viability through the cost reduction as well as environmental protection. However, it is not very effective for the lignocellulosic biomass with relatively high lignin content, such as woody biomass or nutshell or higher lignin feedstock. This process is not recommended for highly lignin content. So the next process that we're going to discuss about the carbon dioxide explosion method. Carbon dioxide can also be used for the pretreatment of the lignocellulose, and it is used as a supercritical fluid under high pressure condition where the lignin gets solubilized effectively. Under the high pressure condition, carbon dioxide penetrates the biomass and results in the increased digestibility of the biomass. It is believed that once the CO2 dissolves in water, it will form the carbonic acid which catalyzes the hydrolysis of the hemicellulose. So the release of the pressurized gas in the digester results in the disruption of the structural biomass and increases the accessible surface area to the enzymes. The low cost of the carbon dioxide as a pretreatment solvent, no generation of the toxins in the process, and also use of the low temperature and high solid capacity are attractive features of this carbon dioxide explosion pretreatment method. However, the cost of the equipment can withstand high pressure conditions of the CO2 pretreatment is a great limitation to the application of the process in the large scale. The next part is the ionic liquid pretreatment method. The use of the various kind of ionic liquids as a solvent for pretreatment of the lignocellulosic biomass has received the great attention during the last decades. Ionic liquids are a class of solvents with low melting point, wide temperature ranges, and high polarities, high thermal and chemical stabilities, non-flammability, and negligible vapor pressure consisting of the ions like cations, anions, and very good solvating properties. The dissolution mechanism of the cellulose in ionic liquids involves the oxygen and hydrogen atoms of the cellulose hydroxyl groups and that form the electron donor electron acceptor complexes which interact with the ionic liquids. The hydrogen bonds between the molecular chain of the cellulose are broken down on the interaction of the cellulose or hydroxyl groups and ionic liquids, result in the dissolution of the cellulose in an effective way. The imidazonium that is salts as an such as various kinds of imidazonium salts are used as a ionic liquid which are widely studied in the fractionation of the biomass. So the organic organosolvent solvation method has also attracted attention and demonstrated potential for the utilization of the lignocellulosic pretreatment method. In this process, a mixture of the organic solvents with inorganic acid catalyst such as hydrochloric acid or sulfuric acid in the aqueous form is used to break down the internal lignin and hemicellulosic bonds. The usual operational temperature for the organosolvation falls in the range of 150 to 200, not that high temperature. So, organic acids such as oxalic acid, salicylic, and acetyl salicylic acids can be used as a catalyst in the organosolvation process. The solvents commonly used in the process are methanol, ethanol, acetone, ethylene glycol, triethylene glycol, glycerol, aqueous phenol, aqueous N-butanol, tetrahydrofuryl alcohol, etc. These are some solvents used in the organosulfation process. Due to the high cost of these solvents, ethanol and methanol are preferred over this kind of over alcohols of high boiling points such as ethylene glycol and tetrahydrofuryl alcohol. Mostly ethanol and methanol are used as a cost effective selective solvents. This process removes the lignin extensively and result in almost complete hemicellulose solubilization by hydrolyzing the internal lignin bonds as well as ether and 4-orthomethyl glucuronic acid ester bonds between the lignin and the hemicellulosic content, and it hydrolyzes the glycosidic bonds present in the hemicellulose and partially in the cellulose depending on the process parameters. So in general, the complete solvent, that is ethanol recovery, is critical issue to the process economy because it may inhibitory to the enzymatic hydrolysis and fermentation or the anaerobic digestion. So complete solvent recovery still is a limitation or challenge. Solvents used in the process need to be drained from the from the evaporator reactor or condensed or recycled back to reduce the operational cost. Next one is the ozonolysis. Sorry, it got disconnected in the middle. The next chemical pretreatment method is the ozonolysis. Uh, so this ozone treatment is a way of reducing the lignin content in the lignocellulosic waste. The main parameters in the ozonolysis are the moisture content of the sample, particle size, and ozone concentration in the gas flow. So it has an advantage that the process is carried out at a room temperature, also at a normal pressure condition, and it does not lead to the formation of any inhibitory compound. However, ozonolysis requires large amount of the ozone, which makes the process very expensive. So it is not recommended for the commercial application. Ozonolysis also has been studied to degrade the lignin and hemicellulosic content in many lignocellulosic materials such as wheat straw, ray straw, bagages, or green hay, peanut, and this kind of popular sawdust. Next process is the wet oxidation process. So wet oxidation is an oxidative pretreatment method in which the oxygen or air is employed as a catalyst at temperature above 120 degrees Celsius. So here the reaction temperature, time and oxygen pressure are the most important parameters in the wet oxidation process. The main reaction that occur in the wet oxidation pretreatment are the oxidative reactions as well as the formation of different acids. This process is effective in separation of the cellulosic fractions from lignin and hemicellulose. So now we have discussed about most of the conventional methods, including advanced method like in introduction of the ionic liquids or deep eutectic solvents as a also incorporating the organosolvation methods. So these are some conventional method. Now we are going to discuss about the emerging pretreatment technologies for the biomasses. It includes the microwave irradiation method. In the last class also we have discussed some of the uh, brief of these physical pretreatment methods. So this is considered to be a emerging technology as these microwaves. These are some electromagnetic radiations with the wavelengths ranging from 1 millimeter to 1 meter. These wavelengths, and they are located between 300 to 3 lakhs megahertz on the electromagnetic spectrum, and these are non-ionizing radiation that transfers the energy selectively to the different substances. So this is the principle of the microwave irradiation. So it disrupts the lignocellulosic structures by breaking down the crystalline region of the cellulose, making it more accessible for enzymatic and chemical hydrolysis. Currently, the microwave assisted pretreatment technologies of the lignocellulosic biomass can be classified into two main groups. One is microwave assisted solvolysis method under mild temperature. So it is kind of a combination or hybrid technology that microwave irradiation assisted with the organosolvation method that depolymerizes the biomass to produce the valuable value added chemicals. Next one is the microwave assisted pyrolysis. This is the thermochemical process, a pyrolysis of the lignin without the presence of the oxygen under the high temperature condition to convert the biomass to the bio oil and biogases mostly. So this microwave hydrothermal pretreatment, one of the other category, it involves the removal of the more acetyl groups in the hemicellulosic content, which may be raised from the hot spot effect of the microwave irradiation. So in case of the conventional heating, suppose we are considering the pyrolysis in a conventional furnace or heating condition. So there the energy is transferred from the outside surface of the material in the insides to the core of the material by the conduction method. Thus, it may create the overheating on the outer surface while still maintaining a cooler region in the inside. So, this conventional heating method or the conventional this conversion method by heating high temperature conditions, this might not be effective for bulk biomass handling. So in contrast to that, when we are using the microwave irradiation method, it induces the heat at the molecular level by direct conversion of the electromagnetic energy into the heat energy. So energy is therefore uniformly dissipated throughout the material, so making it more efficient for the biofuel production. The next emerging technology for the pretreatment is considered to be the ultrasound energy. It is also coming under the category of the physical pretreatment method. The ultrasound is the range in the range of 20 kilohertz to 1 megahertz is used for the chemical processing. It produced the high shear force for proficient fibrillation and degradation of the lignocellulosic biomass. So ultrasound pretreatment of the biomass result in the alteration of the surface structure and production of the oxidizing radicals that chemically attack the difficult lignocellulosic matrix. So additionally, ultrasound can disrupt the alpha oxygen 4 and this kind of linkage in the lignin, which results in splitting the structural polysaccharides and lignin fraction by formation of small cavitation bubbles, and these bubbles formed grow to a certain critical size and then become unstable. And when it becomes unstable, there will be some collapsing of the bubbles very violently, and achieving the pressure up to 1800 atmospheres and temperature of 2000 to 5000 Kelvin. So thus ultrasonic disruption may represent as an efficient green technology for pretreatment of the lignocellulosic biomass. The ultrasound was found to attack the integrity of the cell walls and also cleaving the ether linkage between the lignin and hemicellulose, increasing the accessibility and extractability of the hemicellulose. The ultrasound assisted alkali pretreatment, that is the you can consider to be hybrid technology. Ultrasound assisted with the alkali pretreatment can enhance the lignin degradation enzymatic sacrification rates by breaking down the hydrogen bond between the molecules of the lignocellulosic and lowering its crystallinity. However, the ultrasonic vibration energy is too low to change the surface conformation of the raw material biomass particles. So it is not a vibration energy is not too large because it is only up to 1 megahertz. So it is not too much vibrational energy is being supplied by this ultrasonic condition, but still it is effective. Combining the ultrasonic pretreatment method with ammonia pretreatment, such as a considered as an example of sugarcane, it may resulted in the cellulose recovery up to 95 or up to 96% almost, with 58% delignification. Additionally, the synergistic effect of the ammonia with the ultrasound, it reduces the byproduct formation, and also it enables the treatment to be conducted at a moderate temperature and reduce the cellulose crystallinity. So we can see this kind of emerging technology in combination with the existing conventional technology like ammonia pretreatment or alkali pretreatment methods. This combination of combination or the hybrid pretreatment technology may be more effective or more give more yield for the biofuels for from the biomasses. Next, when we are discussing about the combination of microwave as well as the ultrasound pretreatment method, so these both ultrasounds energies are may be applied to the biomass to reduce the size of the biomass or increase the exposed surface area and increase the availability of the cellulose, hemicellulose, and oligosaccharides present in the biomass, facilitating further processing to produce the target chemicals. So such hybrid approaches was found to selectively it will degrade the waxes and lignin. Also, microwaves are reported to remove the waxy layer from the surface of the biomass to increase the surface area more available for the enzymatic action. In hemicellulosic degradation method, the combination of the ultrasound and the microwave energy was found to provide a supplemental method for heating of biomass internally, which rapidly hydrolyze the hemicellulose. Next, when it is considered to be gamma ray irradiation. It is obtained from the radioisotopes cobalt 60 or cesium 137. It also have been tested as a lignocellulosic pretreatment method. Ionizing radiation can be easily penetrate lignocellulosic structure, causing it modification of the lignin crystallinity and breaking down the cellulose crystal regions. The later impact, that is the breaking down of the crystalline region of the cellulose, is facilitated by the formation of the free radical which decay quickly from the amorphous region after the termination of the radiation. Now, this decay at a certain period from the crystalline region also causes further degradation of the biomass. So next one is electron beam irradiation method. So electron beam ionization radiation is obtained from the linear accelerators. This pretreatment uses the accelerated beams of the electrons to irradiate the lignocellulosic biomass in order to disrupt the structure of the cell polymers like lignin, cellulose and hemicellulose by such processes as production of the free radicals and inducing the cross-linking formation of the chain sections, decrystallization or decrease the degree of polymerization. This also is very similar to the gamma ray or the microwave radiation. So pulsed electric field field processing uses simple device without moving parts that treat the plant biomass or the bio suspensions between the two electrodes with voltage pulses and with the electric field strength from zero point 0.1 to 80 kilovolt per centimeter for a very short time. Under this pulsed electric field condition, the biological membrane is disrupted and local structural changes occur which result in the loss of semi-permeability and allowing it more passage for the intracellular compounds to the surrounding solution. This also facilitates the entry of the hydrolytic enzymes through the pores of the treated plant cell membrane. It was found that the pretreatment of the lignocellulosic material with 2000 pulses at field strength of 10 kilovolt per centimeter could improve the cellulose hydrolysis for conversion to fuels and other chemicals. So till now we have discussed lot of available technologies as a pretreatment method for biomass. So uh, some of the details are being discussed, the process parameters and uh, how it is impacting the selective separation of the lignin, hemicellulose, and cellulose content from the lignocellulosic biomass. So, based on the biomass sources characteristics, we need to choose selectively that what is the best pretreatment method for reducing the recalcitration property of the lignocellulosic biomass. Now, the in the recent advanced pretreatment method, the hybrid technology, that is the combination of this existing technology, one or two process combinations, is giving the more yield or the more higher yield of the product or lesser the degradation product. So we need to do lot of optimization of the processes for selective biomass resources. So now I am going to discuss about the some advantage and disadvantage of the discussed pretreatment technology that we have discussed so far. Uh, First one is the physicochemical pretreatment methods. So this mechanical combination method that we have discussed about the ball milling or extrusion methods or other kind of size reduction equipments. So this increases the surface area of the biomass and it also reduces the cellulose crystallinity by this milling and grinding operation. So, but the disadvantage is that the power consumption is usually higher than her inherent biomass energy. The chemical the sorry ammonia fiber explosion, so it is also considered to be a chemical and physicochemical pretreatment method. It increases the accessible surface area, removes the lignin and hemicellulose content, does not produce any inhibitors for the downstream processes. Also it increases the sacrification rate, but the disadvantage includes it is not efficient for the biomass with the high lignin content that we have discussed. So I am giving the brief of the advantage and disadvantage of the pretreatment technologies are discussed so far. Ozonolisis, so it involves the chemical pretreatment method. It reduces the lignin content, but and it also reduces and it does not produce the inhibitory residues. But throughout the process, a large amount of the ozone is required, which makes the process very expensive. Pulsed electrical field, it operates as ambient condition, pressure temperature condition, and disrupts the plant cells very efficiently. But also it is a very energy efficient process because maintaining the high voltage for this process is very energy intensive, and also it is high costly. Gamma ray irradiation method, it is mutagenic effects in increasing the cellulose activity, but it is highly disadvantage includes high cost of the process and difficulties in the large scale application. Electron beam irradiation, it also increases the enzymatic digestibility because it fragments the biomass into more exposure way, so it increases the enzymatic digestibility, but it also has the limitation of the high cost of the process and energy extensive. Ultrasound, it is obviously a effective method. It is a faster way, and also the main problem or limitation includes the high cost and high energy extensive process. Microwave irradiation, it is better giving improved hydrolysis condition, also the faster process, but also it is having the same issues of limiting factor like high cost and high energy. Next one is the chemical pretreatment, that is the high acid hydrolysis. Acid Acid hydrolysis, it hydrolyzes the hemicellulose to xylose and other sugars, and it alters the lignin structure. But these kind of acids may cost high cost relative because high temperature, high pressure conditions are being maintained, are required to maintain. Also this high also the acid treatment, it may do the corrosion of the equipment for the longer period or longer prolonger use and formation of the inhibitory substance. It is the main limiting factor for the acid hydrolysis. Coming to the alkaline hydrolysis, it removes the hemicellulose and lignin content very effectively, and it also increases the accessible surface area. But the disadvantage is the longer residence time it required, and irrecoverable salts are being formed because of this alkali pretreatment and which incorporated into the biomasses. So it is an expensive process and difficulty in recovering these alkaline bases. Organosolvation method, this is hydrolyze the lignin and hemicellulose in an effective manner, but the disadvantage includes the solvents needs to be drained from the evaporator or reactor and it condensed and recycled back. It should be, these organic solvents are very costly, so high cost is also involved as a limiting factor, and there are some production of the inhibitors throughout the process that may inhibit the later stage of the conversion. So this is the auto inhibition effect is occurring through this organosolvation method. So this becomes a limiting factor for utilizing this or this process in a commercial way. Also, there is low recovery of the pentose sugar. The next one is some of the hydrothermal pretreatment method, that is we have discussed the auto hydrolysis or liquid hot water treatment. It advantages that elevated recovery rates of the pentose sugars and also generates very low amount of the inhibitors. But the disadvantage includes the degradation it involves because of the temperature condition. The temperature condition, high, if it is going to above high temperature conditions, then there is some chances of the monosaccharide sugar degradation. Steam explosion, it is maintained as a very high temperature condition, causes the hemicellulose degradation and lignin transportation very effectively, and it is also a cost effective method. Now the thing is the destruction of the portion of the xylene fraction is occurring due to the steam explosion operation, and there is also incomplete disruption of the lignin carbohydrate matrix that has been found. Generation of compounds, the microorganisms. So the inhibitory compounds are also produced in the steam explosion method. The overall process is not effective for um, complete complete dissociation or degradation of the lignocellulosic biomass. Supercritical CO2 utilization, that is the CO2 utilization, it includes the supercritical fluid high pressure condition. So obviously it is very effective for for increasing the surface area of the biomass. It does not produce any inhibitory compound, but it does not alter the lignin and hemicellulose structure, and it is also highly cost related, because maintaining this or keeping the supercritical fluid CO2, it is very uh, difficult or very cost intensive for this reactor maintain. Supercritical water, better mass transfer occurs, good solvation potential as well, and enhances the enzymatic digestibility. So this production of the inhibitors such as furfural or hydroxymethyl furfural (HMF) or acetic acid, these are some production of the inhibitors. They affect the further chemical conversion of the biomass product. So this becomes the limiting factor. And the enzymatic pretreatment process that comes under the biological pretreatment. So it is very simple. Advantage includes it is very simple and efficient, also very selective in nature. It degrades very selectively the cellulose and hemicellulose content, and it also have high and low moisture containing biomass it can process, and high yield also. But the thing is, these advantage includes it degrades the lignin to certain extent only, and rate of hydrolysis is very low. So this is all for today's class. Is there any question to ask for today's session? Any specific question that you can ask? In the next class, we will be discussing on the mm, uh, thermochemical processes for pretreatment method like pyrolysis, gasification. Those are very important because in the larger scales, where in the refinery or in the larger scales for the biofuel production, we are mainly uh, going for those processes. After the pretreatment method, those are the main processes for producing the biofuel out of the biomass. Those thermochemical processes needs to be discussed in a detailed way. So we will discuss in the next class. So is there any question for today's class?
Okay, so if there is no question, so thank you all for joining for today's session. We will meet in the next class. Thank you.